Hello, welcome back to the channel. Today, we're diving into part 4 of our Unsloth LLM Engineer Interview Coding Challenge series. If you missed our earlier episodes, we've taken a close look at the Unsloth coding tasks, breaking down what they are and the challenges they present. We also explored NF for quantization and dequantization in theory, and looked at the single-thread dequantization NF for GPU device function. Today, we continue the coding task 1, accelerating NF for dequantization. Our challenge is to outperform Unsloth's fast dequantize by at least 15%. To achieve this, we need a deep understanding of Unsloth's existing implementation. Specifically, we will explain a multi-threaded CUDA kernel called k-dequantize blockwise, the core of Unsloth's fast dequantize, focusing solely on the NF4 data type. And guess what? I've got a step-by-step visual guide to help us see exactly what's happening inside the GPU. Let's jump right in. Before diving into the details, let's start with a quick crash course in CUDA. CUDA is a parallel computing framework that allows developers to harness the immense processing power of GPUs. CUDA programs are written in kernel, a function that runs on the GPU and is executed by thousands of threads in parallel. These threads are not independent, but are organized into thread blocks, where they work together to solve computational tasks efficiently. Multiple thread blocks, in turn, form a larger structure called a grid, enabling the GPU to process vast amounts of data simultaneously. To further optimize performance, CUDA threads are grouped into warps, each consisting of 32 threads that execute the same instruction in lockstep. At the hardware level, the execution of thread blocks is managed by streaming multiprocessors, SMs, which are the core computational units of the GPU. When a kernel is launched, the thread blocks are scheduled and assigned dynamically to the available SMs, where they remain until execution is complete. Each SM has its own set of resources, including registers, shared memory, L1 cache, and execution units, which it distributes among the threads within a thread block. Since an SM can handle multiple thread blocks at once, its ability to efficiently schedule and manage these thread blocks is critical for maximizing parallelism and throughput. Now, beyond just understanding the thread organization, it is essential to explore the memory hierarchy of a GPU to really optimize performance and efficiency. Each thread in a CUDA program has its own set of registers, which are the fastest available memory, but are also very limited in number. Registers are used to store frequently accessed variables and intermediate results, and because they are private to each thread, they provide quick access without any interference from other threads. In addition to registers, threads within a thread block share access to shared memory, which acts like a user-managed cache. This shared memory is significantly faster than global memory and allows threads in the same thread block to collaborate by sharing data that might be reused multiple times. This collaboration can dramatically reduce the need to access the slower global memory, which is accessible by all threads across the grid, but comes with higher latency. Global memory, despite its larger capacity, is slower to access compared to registers and shared memory, so developers need to carefully plan and optimize their data access patterns to ensure that memory transactions are coalesced. This means that when threads access contiguous memory locations, the GPU can combine these accesses into a single transaction, thereby reducing the overhead. Later code sections will demonstrate the utilization of the CUDA library for achieving coalesced memory access. Alongside global memory, there is constant memory, which is a read-only memory space that is cached and optimized for cases where every thread in the grid accesses the same piece of data. This makes it particularly effective for storing configuration parameters or lookup tables that remain unchanged during the kernel execution. In the bits and bytes kernel, we will see the scaling factor of NF4 is loaded to this constant cache. In essence, the CUDA programming model is built around a layered architecture where the thread hierarchy and memory hierarchy work in tandem. Threads are organized into warps and thread blocks to manage parallel execution efficiently, and this is complemented by a diverse set of memory types, each with its own strengths and limitations. With these fundamentals in mind, We can now break down the kernel code step by step. We will take a look at the code and the visual guide side by side. Step 1 is all about setting the stage with our kernel launch configuration. In this step, we define the key parameters that govern our GPU operation. First, tile size determines the number of data elements that each thread block processes. Next, num per th, meaning number per thread, specifies the number of NF4 values that each thread will handle, which is directly related to the NF4 block size we discussed earlier. Finally, we set up parameters such as nload, valid items to load, and valid items to store to ensure that we never attempt to read or write beyond the boundaries of our data, even when the data size does not perfectly match the tile size. Our visual guide shows this clearly. We're using a simple example with one thread block containing one warp, but with only 2 threads for clarity. Each thread processes 4 items, making our tile size 8. In global memory, you see our quantized data labeled A, scaling factors in the Ubsmax array, and an empty output buffer called out. In thread local memory, both threads have placeholders, qvals, vals, and local abs max, waiting to be filled. Step 2 focuses on setting up your workspace through variable initialization. In this step, each thread establishes its own mini workspace by first creating the qvals array to retrieve quantized bytes from global memory. Since NF4, normalized float 4-bit, encoding stores 2 4-bit values per byte, the vals array is allocated to be twice as large to accommodate the dequantized floating point numbers. Each byte will produce 2 separate output values. Each thread also initializes its local abs max value, which serves as a scaling factor essential for the subsequent dequantization process. The implementation leverages CUDA's block load functionality, specifically configured for our quantized data needs. We initialize a block load operation that handles unsigned char data using the specified number of threads and items per thread. The block load warp transpose parameter is critical here. It optimizes memory access patterns by transposing data within each warp. This transposition ensures that threads access consecutive memory locations in a single coalesced transaction, significantly improving memory bandwidth utilization and reducing latency. The arrays are now initialized and prepared for the efficient parallel loading and dequantization operations that follow in subsequent steps. Step 3 is loop setup. It might seem like a small step, but calculating valid items to load and valid items to store is essential. These variables are our safety nets, ensuring we never try to access data that isn't there, especially when our data size doesn't perfectly fit the tile size. Our guide shows that in this example, valid items load is 8 and valid items store is 16. Everything fits just right. Step 4 is loading the scale factor, 1 per thread. Each thread needs a scaling factor to correctly convert its NF4 values. Here, every thread loads its own scaling factor from the Ubsmax array. Since each thread handles its own NF4 block, it only needs one scaling factor, not a whole bunch. The math here is simply computing the NF4 block id from the thread id LDG is a CUDA intrinsic for reading data through the read-only cache. Our guide makes it clear. Thread 0 gets 0.12 and thread 1 gets 0.25. Easy and efficient. Step 5 is loading quantized data with coalesced memory access. Using the block load function, thanks to the CUDA library, each thread fills its qvals array with data from global memory. But first, we hit a sync threads checkpoint to make sure every thread is ready to go. This coalesced access ensures that threads pull in consecutive memory locations together, boosting performance. The function efficiently transfers a block of data from the array into each thread's qvals. In our guide, you can see each thread loading its consecutive 4-element chunk from the A array. Step 6 marks the main event, NF4 dequantization, where the heart of our kernel is revealed. In this process, each thread loops through its own qvals array, and for every byte encountered, it extracts 2 4-bit values. The extraction is accomplished by obtaining the high 4 bits through a right-shift operation, and the low 4 bits by applying a bitwise AND with 0x0 f each 4 bits, is then converted into a full-precision floating point number using the dequantize NF4 function we discussed in the last video. Finally, the resulting value is multiplied by the thread's local scaling factor, local abs max, and stored in the vals array. Our visual guide now shows the dequantized values popping up, giving you a clear, step-by-step look at the conversion process. Before writing our results back to global memory, we need one more round of synchronization with sync threads. This step makes sure every thread has completely finished its dequantization work so that no race conditions occur. The guide shows all threads waiting at this barrier, ensuring everything is in order before the final step. Finally, it's time to write our dequantized values back to the global out array using blockstore, another CUB function optimized for coalesced access. Since each quantized byte produces two floating-point outputs, thread 0 writes to out 0 to 7, and thread 1 writes to out 8 to 15. Our visual guide confirms it. The out array is now filled with our neatly processed numbers, wrapping up our process. And that's it. Today, we've taken a deep dive into the K-dequantize blockwise CUDA kernel, exploring everything from kernel configuration and workspace setup to data loading, dequantization, synchronization, and final storage. We've seen how a single-thread dequantization function can be scaled to a massively parallel process, showcasing the true power of GPU programming. If you enjoyed this walkthrough, please give this video a thumbs up, subscribe, and hit that notification bell so you never miss an episode. Thanks for watching, and I'll see you in the next video.